All right, Chem 30s, what we're going to do today is look at buffer solutions in acid-base reactions. This is a brief introduction. So in university, you're going to go through the Hasselback equation, and usually when we set up a buffer system, there's a certain pH we're trying to maintain, and there is a formula for that. In Chem 30, however, we don't have to go into that great length and detail. All we want to know is what a buffer is. So we'll start off this video by asking, what is a buffer? So what a buffer is it's a weak acid and its conjugate base system in an acid-base reaction that resists pH change. And that's kind of the highlight here. What it's going to do is resist a change in pH. When bases and acids react, they neutralize one another, so there's often a drastic change in pH. But what we want is for this thing to settle down. One of the signs that equilibrium has been reached is that you have a constant unchanging pH. So buffers are going to help us get there. So once your reaction proceeds forward or in reverse, the buffers that are present, or the weak acid and conjugate base system in the reaction, is going to work towards achieving equilibrium by keeping that pH constant. This is the acid-bases system's way of applying Le Chatelier's principle, which is that you're looking for a constant rate between concentrations, and more specifically with pH changes. So we want the reverse to equal the forward. Buffers or buffer systems require two things. The first is a weak acid and its conjugate base, and it doesn't have to be in that order necessarily. You can have the base listed in the reactants and the weak acid listed in the products. Just we need both of these present somewhere in the entire system. And the second thing that this needs are equal amounts, and usually we refer to amounts as concentrations, but equal amounts of the weak acid and its conjugate base present in the equilibrium system. And what that means is that buffers will work, so they'll maintain the pH of the solution when small amounts of acid or base are added. If too much of either, so the acid or the base, are added, then the buffer capacity is exceeded and the pH changes, which means that it will not hold the pH constant anymore. So if these two prerequisites are present, where you have a weak acid and its conjugate base, and they're both in equal amounts in the final solution, then within a certain limit or a certain capacity, they're going to maintain the pH of the system. So when we look at this first example here, we have ammonia gas reacting with hydronium, and this would be aqueous. This could be aqueous as well. I said gas, but we can make it aqueous. That's fine. And it'll yield the following products. So, is there a buffer system? Well, let's see if there's a weak acid and a conjugate base pair present. So this goes back and forth. So here, your hydronium ion is a weak acid, and its conjugate base is over here. So there is a buffer system between H3O plus and H2O. And so this pair is going to help maintain the pH of the system. Now remember that it can be in any order. And so we have another buffer system present here where I have NH4 plus, which is also a weak acid. It's a conjugate acid, but it's still a weak acid. And its conjugate base is NH3. And so this is another buffer system, which is going to do the same thing. Okay, it's going to resist a change in pH. Now, The fact that there's two of them doesn't make a difference. At least one buffer system must be present for this to work. So the fact that there's two is irrelevant. Just one of them will do the same thing. And so a typical question would be, if I give you an equation like this and I say identify a buffer system, or if there is a buffer system, then what would that be? And if you list any one of these, so some good follow-up questions would be, if some HBr is added, what's favored? Okay, well, HBr, remember that that's going to break into H3O plus and Br minus. Br minus is not going to affect the system at all, but H3O plus is on the reactant side, so we're going to say that products will be favored, right? Because we're increasing the reactant. So products are favored. Remember, we could also say it shifts right. Products are on the right, so saying it shifts right is the same thing as saying products favored. Now, will the pH change? Well, the answer is no. And why? Well, because we have a buffer system. So, in this same, a similar question here, we got phosphoric acid mixed with ammonia solution gives us dihydrogen phosphate ion, H2PO4 minus, plus ammonium solution. Okay, so is there a buffer? Well, when we look at H3PO4, it is a weak acid, and its conjugate base is over here. So is there a buffer system? For sure. It's H3PO4 and H2PO4 minus. And remember that you could also go this way as well, and that would also suffice as long as there's a buffer somewhere. So yeah, we got our buffer systems there. Now what would happen if H3PO4 is added? Well, if H3PO4 is added, that's on the reactant side, so products will be favored. Okay, or you could also say that it shifts right. Okay, will the pH change? Well, if a small amount is added, the answer is no. And why? There's a buffer system. Okay, right over here. So, to kind of sum this up, and we'll write a question, when can we recognize buffer systems? And the answer is, if there's a weak acid and its conjugate base present, there's a buffer. Okay, so we've seen buffers all along. We just didn't recognize them. Now we're recognizing them. And this is what helps keep our pH constant and maintain our solution at equilibrium.